presenting Predictive 6G. We have Krisa Papagianni from University of Amsterdam that will be presenting on behalf of Desire 6G, and then we have Joachim Sachs and Gurev Pratek-Sarma from Ericsson and KTH that will be doing a joint presentation on Deterministic 6G. The program that we have for today is this very quick introduction. I will be trying to do it even less than 10 minutes to allow more time for the actual discussion. And then we have one presentation per project. The idea is that in this webinar series, we will be having each event kind of focus on a theme. So presentations are around that theme. In this case, is the architecture and enhancements that each of the projects are working on. And then we have a short panel at the end around this theme. So in this case, we have a presentation from Peter on multi-domain deterministic service management architecture from Predictive 6G. Then Krisa on towards extreme network KPIs with deep programmability in 6G from Desire 6G. Then Joachim and Gurev on 5G latency analysis and possible improvements from Deterministic 6G, and then the panel at the end. The way we are going to handle questions is that please you guys do it on the chat, and we will be handling the questions at the end of each of the presentations to manage it, to try to manage the time as best as possible. And after that, I'll try to, if we have more questions that we can accommodate, I apologize in advance, but I think we should keep the time so we have at least some time at the end for the panel. And even in the panel, we can also address some of the pending questions, if any. And with that, I think we can just directly go into the first presentation from Peter. So Peter, the floor is yours. You can start whenever you want.
Thank you very much. And okay, I'm sharing the screen, hiding the bar, putting full screen. So let me know if you see the presentation in full screen and also you can hear me.
Yes, we can do it.
Okay, thank you very much. So my name is Peter Szilágyi. I'm a researcher at Nokia Bell Labs, Hungary, and I'm also technical manager of Predictive 6G. So in this webinar, I'm going to present multi-domain deterministic service management architecture, which is kind of the focus of the Predictive 6G project. The outline of the presentation is that I will give an overview of what we are working on as a project, as a Predictive 6G, what's kind of the mission of this project. Then I will introduce the concept of multi-domain deterministic services and contrast it with regular single domain technologies. Then talk a little bit about the data plane, because that's required, some level of understanding of that is required to appreciate the control process management plane architecture that is kind of stitching all the technologies together to enable deterministic end-to-end services. And then Q&A discussion in the remaining time for the presentation. Okay, so the vision of Predictive 6G is to enable and provide deterministic services over multiple networks with different technologies, for example, 3GPP, TSM, Wi-Fi, and potentially others. So what this really means is that instead of focusing on to enhance the determinism, let's say jittering or time sensitivity of communication services within a specific technology, we are more focusing on how we can connect different technical domains with even different level of deterministic enablers together and provide end-to-end service on top of multiple one of these. And that's why Predictive 6G is kind of a management project, first and foremost, a multi-domain management project, with, of course, a very deep focus on time-sensitive and predictable and deterministic aspects. So these are even kind of the pillars of the project: end-to-end reliability, which means high availability, low packet, or basically zero packet loss, failure tolerance in end-to-end. All of this in end-to-end, that's very important. End-to-end time sensitivity, so time-sensitive traffic like robotic control or even some audio-visual video type of use cases. Digital twin to physical twin and replica synchronization. These are use cases which require time-sensitive enablers on the data planes on the networks, and to do it multi-domain across different domains, that's kind of the challenge we are taking. And also predictability, which is part of the project's name, means that the network is not just retrospectively acting on top of already detected even, but also tries to forecast what would be the resource availability, what would be, let's say, the potential service quality along different alternative routes, for example, in end-to-end, and choose accordingly to kind of provide the best potential service in terms of determinism. And that requires, of course, using data collection, analytics with AI and digital twinning and all of these technical enablers. And these are actually the pillars making the big technical progresses within the project. So one is, of course, to look a little bit into the individual components of technological domains, like what's happening in TSM, what's happening in 3GPP, IETF, all of these traditionally existing technological domains, networking technologies. And if possible, maybe enhance them a little bit, but more importantly, to provide programmability on top of these to enable the development of a multi-technology data plane, which consists of not a single technology, but multiple one of these existing next to each other, and providing consistent delivery of packets according to deterministic principles. And that kind of harmonization across the different domains kind of requires that we have a digital twin AI-based analytics service, which is acting as a control/management plane of this MVP, and is able to distribute, let's say, service responsibilities across different technological domains, so that in end-to-end, what the end-to-end service provides is according to the needs. And that is in a dynamic situation, so you cannot just predefine numbers, values, thresholds, attributes to a service, because that depends on what is the, let's say, dynamic network condition, user mobility, additional traffic that the network has to serve. Therefore, we need kind of closed-loop automation of all of these domains and also an end-to-end vision. Now, all of these considerations kind of lead into a reference architecture that we are defining in Predict 6G. One word on why it's reference architecture. It's because we are defining kind of all the enablers or a reasonable set of enablers, data plane-wise as well as management-wise, which can accommodate an automated management of establishing and managing and assuring end-to-end deterministic services over multiple domains. But of course, any particular network deployment might be a bit different, and having or lacking specific enablers, let's say in the data plane. For example, some network deployments will have, let's say, no Wi-Fi part or no 3GPP part, or no IP in between, or TSN instead of one of these. Therefore, the reference architecture means that how we envisage the general architecture of being able to manage multi-domain deterministic services will be adaptable, instantiable to any specific deployment. But of course, it will need to take into account what are the existing particular capabilities, like topology, potential deterministic enablers per domain, what devices are there, how they can be programmed. So all of these needs to be kind of integrated into an actual implementation of the architecture. But on the reference level, this is how we envisage. So as I said, multi-domain is in the key focus of the project. Just by examples, to consider 3GPP, that network I could have probably put TSN there and Wi-Fi. And these are kind of management scopes for Predict 6G. Why? Because these are existing technologies. So we have not invented 3GPP. We have not invented Wi-Fi and the others. We are leveraging what they can provide, also trying to enhance per domain, but also leveraging what they can provide. Therefore, these will be programmed, managed by those services that we define in Predict 6G and put on top of the domains and on top of the end-to-end. And this is actually the architectural vision that on the service level, all of these network domains or technological domains are capable of some type of service provisioning. At some domain, it's very well defined, like what's a 3GPP communication service, it's very well established. Maybe in Wi-Fi, it's not that much, on the surface, it's not that much articulated what is a service, but there are components in the Wi-Fi as well, and also in IP and the MPLS or DetNet that kind of represent services like traffic flows with a given quality of service between endpoints. Basically, that's what abstractly a service means. And though there are domain and technology-specific means of establishing, assuring, navigating the services, those are the things that we are leveraging in order to stitch together so-called end-to-end services. End-to-end for us means that potentially devices which will communicate with each other in a deterministic manner are attached directly in different network technologies. For example, a 3GPP terminal, like a smartphone, will be able to speak in deterministic manner to other device attached to a Wi-Fi access point, because of course the two networks will be connected in the back end, but the primary connectivity, the last mile connectivity is different. So this is in contrasting potential other project focus that is, let's say, improving how 3GPP quality of service lives up to deterministic requirements alone, so within the 3GPP. So considering these end-to-end services, we need to then think about how we can manage these, how we can automate the establishment of the individual services, these ones, so that end-to-end services are created that would provide required set of quality of service attributes, deterministic ones. And in order to make the architecture extendable, which I also refer when I bounce back with the actual management service architecture towards the end of the presentation, just an idea I want to plant here already is that, of course, each of these network technologies have very specific control and management capabilities and APIs and tools, and to different level of development. Again, 3GPP seems to be very well developed in terms of like whole work group is determined to managing 3GPP services, whereas Wi-Fi network management is usually non-existing or access point based or vendor specific. Different proprietary techniques exist, of course, and therefore what makes these really distinct also would make it very challenging if you just want to have, let's say, a single management entity which is able to talk to 3GPP, Wi-Fi, .NET, and all the other potential technologies that you want to bring underneath the umbrella of Predict 6G. So just complexity on top of each other. Rather than the idea in Predict 6G is that we conceal the complexity, the technological complexity, the programmability complexity, the API complexity, or even the lack of correct and well-developed APIs in a particular domain with a so-called management function that we have defined in Predict 6G. Like 3GPP management function has the role of knowing the 3GPP APIs, for example, network exposure or NWDAP if it's in trusted domain, or whatever is the means of, or O&M systems towards 3GPP, which enables an entity to configure 3GPP network into providing different types of services. Talk 3GPP downstream and southbound, and then expose abstracted capabilities that, yes, I'm able to establish a 3GPP service between this terminal and that data network with a given level of determinism. And that is the level of information which needs to be then provided towards the so-called end-to-end management function, which does not need to know the technological details of how a 3GPP service or a .NET service, Wi-Fi, whatever service comes by in the technological space, but knows in an abstract level that the domain-specific service exists. And with what capability? What would be, for example, the intrinsic delay that is at minimum will be suffered by all the packets because of the technological constraints or the topological constraints, and be able to calculate with that when an end-to-end has to be broken down into domain-specific sub-services. Be able to assign responsibilities, how much of the delay budget, for example, is attributed to one or the other of the domains, so that in end-to-end, it still fits within the end-to-end delay budget, or the latency, or the jitter target, and so on. This is the role of the end-to-end. And likewise, 3GPP MF is talking to the 3GPP APIs, then .NET is talking to maybe CNC, Wi-Fi is talking to whatever is the available Wi-Fi management node. It could be a cloud-based centralized Wi-Fi manager, or even the access point itself, again, depending on the particular deployment, referring back to reference architecture. And with this architecture, it's flexible enough to be able to accommodate any new type of network technology as well, like Profinet or even wire domain. which might be already existing, but lacks the integration into something that would enable wired and wireless coexistence in an end-to-end manner, like in a legacy factory deployment. So this is then, of course, completed with a means to interact with the kind of the architecture. Like somebody has to tell this Predix 6G management architecture what services should be existing, for what purpose, with what level of service. And that would be user or application or an operator even. So I will detail it a bit more, but obviously with any automated management architecture and management services that we are defining, there needs to be governance left for the operator or for the users of the system. It's not the system that will somehow dream up what services are required, but it will respond to service requirements or service intents coming externally by end users or by the operator of the network. And then those services are orchestrated and assured automatically within the system. Now, going a little bit in the service direction, because that is the more essential idea, let's have a bit deeper view on what services are really in Predix 6G and why they are end-to-end, or why we are calling them end-to-end. And just to bounce back this idea that they are requested by operators or end users, and then what are the components? So what is the definition of a service? What needs to be provided as an input to the Predix 6G system so that an end-to-end service will be then delivered automatically by the system? So and on just high level, logically, service endpoints. Where should the service be provided? We are now focusing mostly on end-to-end, point-to-point services across potential endpoints that are located in different network domains. But of course, the idea is very easily generalizable to point to multi-point or group communication type of services as well. Basically, somebody has to define the service area or the entities among which the communication needs to be deterministic. That's one. Then the second one is, of course, what determinism is required. That is defined by the use case. Often that is derived by the capabilities of the communicating endpoints. Let's say if a robot is communicating with its PLC, usually it's defined and they are known in advance. Let's say what latency is tolerated, what loss, what reliability is required to sustain the production or whatever mission that the robot is providing. So quality of service characteristics. Then not necessarily, but it would help the system if traffic characteristics are also known. Like I said, it's not mandatory, so the system can live without that. But usually when deterministic traffic is required, so deterministic service is required, then the traffic is not, this bulk, any type of infinite download or random pattern. Usually there is very stringent pattern within the traffic. It's a periodic traffic, usually with a given time cycle, or kind of a superposition of multiple ones if there are multiple processes talking to each other between the endpoints, but it's very well regulated. If it was not regulated, then determinism would not probably be required. You will never require deterministic service for being to download YouTube over the internet. That's working very well over elastic services. But you will require deterministic services to ensure that your robot digital twin is in sync with the physical one, so that you can trust it with manufacturing a piece of a workpiece according to the, let's say, the drilling process or whatever is needed. So that's kind of the scope of the deterministic services. Traffic flow template is basically telling the system how to recognize that traffic. So it could be very easily associated with tuples, port numbers, whatever is available. So ideally, some description of the traffic is available in advance. Of course, you could think about deep packet inspection type of techniques to infer what packets belong to the deterministic service, but that is not really efficient in reality, and this is therefore not within the scope of Predix to create those type of techniques. We assume that it is known to the system how to isolate out the traffic that needs to be treated deterministically. Of course, other traffic can also go to the system. So it's not saying that all the traffic has to be deterministic, but the deterministic part has to be recognizable by the system. And then service lifetime, very intuitive one. So when the service needs to be provided, maybe it's a permanent service until it's revoked, okay, but maybe it's a periodically established service that only needs to be alive during, I don't know, some production time in the factory or whatever is the constraint. So it should be possible to provide that to the system. Why it's needed by the system? Because let's say if you define a service, but it's only active between 8 to 4, then the system will be able to use the resources after 4 o'clock for something else, for another deterministic service, for example. So it leads to more efficient resource allocation in the end. So these are kind of the end-to-end services that we're entertaining. And if you put them up on a basically on a picture, then you could say that end devices, it's between end devices. So an end-to-end service is between so-called service endpoints in end-to-end. And of course, in a degenerate case, the service endpoints could be just next to each other, attached to the same network. That's of course also handled by Predictive 6G. It's not like, yeah, but if you don't have at least 3 domains, then you are not able to do Predictive. No, you can of course do that, but that's the true power of Predictive 6G is coming up when you have multiple domains. And if you want to orchestrate autonomously services across end devices which are located in different network domains. Now, I said earlier that, of course, the different domains will provide constituent sub-services or domain-level services, because that's how the technology works. So if you don't want to disrupt the whole technology so that you redefine all the existing networking domains, which of course cannot be done, then a pragmatic approach is that each domain will be providing its own service between endpoints that are located within the domain, because that's what that network technology is useful for. And that domain service can already be time sensitive or can already be deterministic. If that domain is, let's say, a TSN domain, then the TSN capabilities are leveraged to provision the right level of determinism between yellow per domain service endpoints. But the challenge is actually is that then the next domain, let's say domain number 2, which is maybe not a TSN network, might be a 3GPP with a radio and backhaul and stuff, should also contribute to the level of determinism, or at least not disrupt or not degrade the determinism that was created so far. And therefore, its own quality of service capability should also be provisioned. But probably that's via different APIs with different tools and so on, like I mentioned. That's why we need to have this domain-specific management architecture in the end. And likewise, as many domains are participating or are located in between end devices, they all need to establish their own services so that logically an end-to-end service is created. The challenge is what happens between domains, domain borders, when actually the same data packet has to be forwarded from the responsibility area of one domain to that of the other. And if you look for the future, let's say, what would be technologically the most reliable way of doing that if there are so-called border gateways or gateways basically between domains. Gateway means kind of a network node which has interfaces in both of the domains or multiple of the domains. We could have border gateway across more than 2 domains as well, of course. And then those nodes, like routers, logical routers, would be provisioned on an interface level with the right configuration, one configuration that is facing one of the domains and the other which is facing the other domain. So then within the device, of course, the switching of the packet could be done very efficiently, and then there is no degradation of any deterministic level of determinism which was handled in the domain 1 or domain 2. And if you have this border domain or border gateway concept, then it's also possible to, at least logically, easily scale data plane reliability techniques to work in end-to-end, end-to-end meaning again across multiple domains. And one very good example is this pre-off, or okay, FRER if you look at the frame level, or pre-off if you look at the packet level. Elimination and duplication or replication elimination. Basically, multiple paths in end-to-end carrying the same traffic in order to survive without any drop in the determinism, any single point of failure, except maybe the end device. But if the end device is gone, then the whole thing is gone. Traditionally, these mechanisms are domain specific. So you would have like maybe in TSN, you would have a FRER, frame replication, between the domain endpoints within the TSN domain. But the two paths within that would join at the beginning and at the end of the domain as well. So if the domain endpoint, domain border would be the point of failure, then the multiple paths within the TSN domain would not help in end-to-end. But if you have border gateways and multiple one of them between each domain, each adjacent domains, then you'd be able to really truly have in end-to-end disjoint paths for the packets. Of course, all of these need to be configured. That's why we need that AICP on top of the data plane. But you would be able to have it orchestrated automatically and have a truly resilient, in end-to-end, really resilient deterministic service, which survives any single point of failure. And of course, you can have multiple protections if that's a very, very mission-critical service. So that is just as a glimpse of logically what are then end-to-end services, how they are broken down into domain-specific ones, and also what are the challenges on domain borders that we are tackling in the project. Now, one maybe just a few slides on more before I enter the kind of towards the summary. I'm also looking at a little bit of. No, I think I can still spend a few slides on the services. So I mentioned deterministic services, and I mentioned one of the descriptor factors or description items attributes is quality of service characteristic. Now I just open up a little bit more what is quality of service for deterministic traffic, and basically it is a bit tricky because of course there are those traditional metrics that are very general. Any traffic would have, let's say, bandwidth or a throughput and latency, and some of these is really in the realm of let's say deterministic quality of service, and some is not that much important. For example, throughput is usually not the primary metric by which you would characterize a deterministic traffic. The reliability, the jitter, meaning the time sensitivity, the latency, and end-to-end, those are more important. And usually the amount of traffic that is carried is not overwhelming. So it's not like you need to transmit hundreds of megabits per second traffic and ensure determinism on packet level or no jitter on packet level. Usually the amount is not that much pronounced. And therefore the key parameters which characterize deterministic service are what's considered now on the slide. So, okay, priority is just to be able to, resolve or deconflict services in terms of, resource scarcity, but reliability, which is meaning protection against failures, packet loss, which is usually zero. The requirement is to have no packet loss. Jitter, again, the requirement could be very, very low or almost, virtually zero. Of course, there's no such thing as zero in real network, real measurement, but virtually zero. And then come interesting things like how you measure latency or delay, what that really means. Because we talk about delay sensitive traffic, but okay, what it really means. Different traffic patterns enable different types of delay or latency definitions. And if you have, let's say, a traffic flow from one direction, like a unidirectional traffic, then what you can measure logically is basically one-way delay, or one-way delays at multiple interfaces, or between multiple interfaces. And in that case, you can measure also the end-to-end delay from one endpoint to the other endpoint. And then that would be the target. That's what is required from the system. Now, some other traffic patterns or applications are more transactional, meaning that one endpoint is submitting, let's say, a request, and the other endpoint is providing a response to that. And this request response transaction is what is on the business or application level has to be deterministic. So that, let's say, the time between issuing the request and receiving the response is deterministic. The jitter would, or the delay actually would mean that one, and then the jitter would mean, which means delay variation, would ensure, zero jitter would in this case would ensure that the transaction time is consistent. And it's important that some applications require really that they don't care if the response was delayed or the request was delayed, or the request was very fast and the response was delayed, then it's still good because in the request response you got the same delay. You can have kind of some freedom even in the network to to ensure that the end-to-end rebouncing of the message is expedited to catch up with some delay that was suffered on one of the directions. So these are delicacies in what deterministic traffic looks like, and what are the KPIs that are really important for an end application that is requiring a deterministic service, and therefore those could be represented in the predict as well. And another thing is that I mentioned most of the deterministic applications of traffic is periodic, because the whole deterministic requirement is coming from kind of a hardware cycle, which is going to interpret or read, let's say, a hardware buffer just at given predefined times. And therefore, the communication network needs to ensure that the message is there to be read out from the buffer, that the hardware works. It cannot deal with any jitter in the network. And therefore, if traffic is periodic, then we can also talk about bursts, which means that what is the amount of traffic that is, let's say, sent like back to back if we are talking about packets, and is there any tolerance in how that burst is being shaped by the delivery through the network. So we can define some extra KPIs or quality of service metrics like burst arrival time window or burst completion time window, which gives again either extra limitations for the network to cope with, but also describes better the service that is required by the Predict6G system. And of course, this all refers again to the end-to-end delivery. So one of the challenges is that it's not like we are having a single technology domain which understands the concept of jitter, end-to-end delay, round trip, burst arrival time, and all of these, and you just tell them the numbers that you receive from the operator or from the end user, and it will be done by the technological layer. Different domains understand, usually deterministically enabled domains, understand similar concepts, but they are not called the same. They are not provisioned by the same APIs. Sometimes you have to provision multiple things so that they add up to, let's say, the jitter. That's kind of the adapter layer that we have to maintain in the Predict6G architecture. That's also one of the reasons why we have to have domain-specific adaptations of how we provision domain-specific deterministic service. So these are the quality of service characteristics. Then what is a service in terms of life cycle? So when they are created, what phases they go through until they terminate. So a service comes by, as I said, when somebody asks for it, like with any communication network, it's usually the case. So the first step in the service life cycle, we can say, is a service ingestion or service request. That's when the service request is received by the system. It can be accepted, rejected because of, let's say, capability or resource reasons. One example is that if, let's say, the minimum delay that would be given along the path, because that's, intrinsic delay of the technology, propagation delay, whatever, and somebody is asking for a lower delay, still it's not possible. For physical reasons, it's not possible. So that's not a valid request. But also it can be that there are already 10 different deterministic services and all the bandwidth is fully consumed, or all the other compute resources or buffering resources are fully consumed, or even just IDs or queues as a finite resource, they are exploited and therefore it's rejected. That's why priority is considered also as one of the so I'm not the quality of service per se, but as an additional attribute associated with the service, so that the system can know them one service is more important than the other, and then it can preempt or terminate another service to make room for a new one. So it's all possibilities. It's kind of general service management stuff. Then comes if the service is accepted, then the service fulfillment is done. Fulfillment means to put in place all the mechanisms that are needed to basically forward the first end-to-end packet through the network or different network domains with the right quality of service. For example, you have to go to different domains and ask them to establish their own concept of a service, and with the right quality of service metrics that are understandable by each of the domain. And potentially in the control set management plane of Predict 6G, some capabilities are instantiated, like a data collection service or a data analytics service, which would be needed to then analyze whether the measured service quality is up to the request or what was requested, and then do proactive changes. So all of this machinery that would be then needed for the next phase of the service, which is the service assurance, need to be instantiated. Maybe you have to fire up a virtual machine, or maybe you deploy a container in a VM. So service assurance is about kind of closed loop automation of making sure that the service remains operational according to the request. So not just kind of a one-time provisioning activity, but continuous monitoring, and if required, a proactive assistance in changing the service parameters. Let's say going to one of the domains and ask to deliver it even lower latency, or even talking to a scheduler and saying that, hey, please restrain the background traffic, which is not deterministic, even more, because we need to make more room on the physical resource level for the deterministic services, whatever that is needed. It's all kind of a reconciliation loop, which is looking at the requirements, which are kind of articulated through the service request, and comparing that with what actually is happening. And this is where digital twins play a role, because they kind of represent have a digital representation of what is happening in the physical network in terms of resources, in terms of services, qualities, and also know digital twins usually model capabilities in the network, like what can be changed in the network and what outcome that would deliver. So you can calculate different strategies in mitigating predicted or actually happening degradations. Hopefully no actually happening degradations, but more like predictions that require proactive changes in the network configuration to prevent that any visible degradation is happening. And then, of course, services will have to come to an end at some point, either because it was kind of like open service, but then somebody asked for the termination, maybe the owner of the service, of course, or that was already provisioned with a deadline. Then service is terminated, which of course requires that all the resources are freed up, and let's say if there was any dedicated monitoring or management service that was instantiated just for that particular service and nobody else needs that, those can also be terminated. So it's like a resource cleanup throughout the whole system, a Predict 6G system. So that's how services born and terminate, and what's happening in their lifetime. Maybe I'm just showing one more picture of the data plane, not for scaring anyone, just to highlight a little bit the complexity of the task.
Sorry, Peter, we need to start wrapping up if you can.
Okay, I will then wrap up. I was just looking at the time. I will just show then one more picture as a summary of the management architecture, and then one more as a conclusion. Would that be okay? A few minutes.
Yes.
Okay. So again, bit wrapping back the management architecture. So now we understand hopefully a bit more what it means to have, let's say, a 3GPP network or a .NET, Wi-Fi, PSN, whatever else, different technological network segment in the data plane, and why it is, kind of a challenge to establish an end-to-end service which has to go through multiple of these technological domains. And like I said, that's kind of the the overall management architecture that we have defined in Predict6G, to have an abstraction of the domain, which is the implementation of that abstraction is, of course, depending on the technology that is down there in the domain, but provide a uniform abstraction of what a domain with deterministic capabilities is providing, like an abstraction of the topology, an abstraction of the services, of the resources, and be able to answer to questions like, can you provide a service between these different endpoints with a given level of determinism? And that helps, actually, that enables the end-to-end management domain to make decisions on new service requests, like selecting the right domains that need to be constituent of the end-to-end service and provisioning the right service configuration for them. That's the overall architecture. And just for illustration, each of these domains, like the end-to-end management domain on the top, and then any of the technology-specific domains are further sliced into so-called management services, just for the sake of being able to provide focused capabilities in like separation of concerns paradigm. For example, just a few examples. Wrapping up this is that, of course, talking about time-sensitive networking, one of the key requirements to even establish any service in the end-to-end is to have time sync across the domains. So we have to provide management of the time sync. We also have to collect the measurements that would enable service assurance, service exposure, and service automation together enable new services to be deployed, and then those services to be maintained with the right level of capability. And there are a few extra kind of management services that we have defined, and we also, of course, define the workflows, how they interact together in the service lifecycle to ingest the service in the end-to-end, and then propagate this down there in the technological domain to establish the service, assure it, and then in the end terminate. So that is kind of the wrap-up, and I guess if you have time still for a few questions, then we can take it now.
Thank you, Peter. Yeah, we have one question on the chat. I don't know if you can read it, or I will.
I will check if I can also access the chat more.
But basically, I can read it.
Please read it.
Argran is asking, for multi-technology, multi-operators, heterogeneous domains, how to establish end-to-end path while taking into account the QS settings end-to-end. So how to define SLA for end-to-end QS?
Yeah. So actually, the framework for that is that the end-to-end service is defined, kind of asked, let's say, requested by defining a set of quality of service parameters. That is the expectation that should happen between the two endpoints, like the two green endpoints. And then the question is, because you are not talking to a single network which can just provide what you have asked, you have to break it down into domain level responsibilities, which will be provided by different technologies. Let's say one is provided by 6G-PD network, the other is by TSN, and so on. And this breaking down, let's say the end-to-end delay request is 20 milliseconds. And then how much can be left for domain one, like 5 milliseconds, and this is 10 milliseconds, and this is also 5. How to split it, what to ask, and by what quality of domain-specific quality of service setting you can ensure that that delay or whatever KPI will be provided. That is what is ongoing in the implementation of these domain-specific and end-to-end management services. The responsibility to define what should be provided by domain-specific services is in the end-to-end management domain, based on knowledge collected from the management domains per technology. What can you do? What are the potential endpoints? What are the potential latencies between the endpoints, and so on? Now, how that knowledge is generated in the technology domain-specific management domains or management services, that is a bit implementation specific, because usually this requires talking to the right APIs, management of the network, or talking to probe system, which is sourcing the data, So this is the adapter which mines out this information, renders it in kind of a uniform data structure, and sends it up to the end-to-end. So the end-to-end doesn't have to deal with the implementation specifics of sourcing information about potential quality of service capabilities per domain, but can be left with the complexity of distributing service responsibilities across domains. And when the Predix 6G defined management domain receives that in this particular domain, you have to create a service with a set of parameters which are tailored, knowing what other management domains will provide, then the responsibility of this one is only to talk to the right APIs in this particular example, the 6G-PD network, and ask for, let's say, a PDO session mapped to a 5QI in terms of 5G quality of service architecture with a packet delay budget provisioned according to the end-to-end request, domain-specific request, with a preemption capability or whatever is kind of coming out of the domain-specific responsibility. And if that's across operators, that also means that the domains are not just technologically separated, but also administratively. And this is kind of also taking this separation of the domains also take into account that maybe the entity governing this one, so northbound interface of this network is actually managed by a different like legal or organizational entity. But of course, if you technologically want to connect different domains, then the kind of the authority has to be given to logically to an end-to-end responsible entity. So you cannot say that you don't allow any access from externally to your network configuration, but you still want to have automatic end-to-end service establishment. The two is not possible.
Okay, thanks a lot, Peter. We also got another question that is, not technical, it's about whether we are going to share the slides. I assume, Peter, you don't have any problem sharing the slides, so we will...
No problem, of course.
We will put it somewhere and we'll share that with the attendees. Okay, thank you very much, Peter. So now we can move to Krisa presentation. So Krisa, whenever you are ready, please start.
One moment. I think you can see my screen, or not yet.
Not yet. We can see you, but not your slides yet. Now, yes, we can see.
If I can.
No, now it works.
Okay, just give me a moment because I need to remove the Zoom thing. Okay. Right, so let me start. So I'm going to start say a little bit about the project, its scope, and the innovations before I go more deep into the architecture. So Desire 6G is essentially a 3-year project. We're halfway through. We're almost halfway through, not yet. So the architecture is not yet published. It's not yet out. It's basically is in stream B. It's focusing its research on the 6G system architecture with a consortium of 14 partners, and unfortunately the technical coordinator Ericsson, Gergely from Ericsson, could not be here today, so I'm doing the presentation on his behalf. So what is the scope of the project? For Desire 6G, our goal is to try to meet performance requirements for real-time mission-critical applications that require essentially lower latency, higher reliability, that's basically what is currently offered. So in that sense, we are trying to design and develop, prototype a zero-touch control management and orchestration platform that has native integration of AI with the goal to support such extreme application requirements, hyper application requirements, over performant and measurable and a programmable, fully programmable data plane. And in that direction, we're looking into 2 representative use cases for 6G, which is essentially an immersive surveillance and inspection application an augmented reality application, and a corresponding industrial application of a digital twin. And this is what you see here on the slide. Basically, you see the surveillance application on the Arnold testbed in Pisa, and on the right-hand side, the digital twin application that is currently, the use case that is currently being developed in 5-tonic. Now, what are the main key innovations? We're talking about, I talked about deprogrammability, about zero-touch network management network. So what we're basically focusing is how we can provide this data-driven autonomic networking, which will be enabled through an orchestration, management, control, and data plane in this R6C. And towards that end, one of our main propositions is basically the use of an end-to-end programmable data plane that supports multi-tenancy, which through using an appropriate hardware abstraction layer can seamlessly interact, the upper layers can seamlessly interact with heterogeneous devices like GPUs, FPGAs, ASICs, and whatnot. The overall goal is to be able to provide flexibility, first of all, in function of placement and offloading, and also to allow us to customize network behavior depending on the slice, following the deep slicing, let's say, approach, considering, of course, performance on one side of the devices and power efficiency. Now, motivated, also enabled by this functionality, we also propose use a pervasive monitoring system where essentially we're stretching up monitoring up to the user equipment. And in this regards, we're utilizing telemetry solutions in order to be able to get more accurate and more information. And in that direction, data plane programmability supports, helps us by providing appropriate, as we can use appropriate in-band network telemetry solutions. I'm also saying here privacy, because we're also looking into approaches of how, for example, we can transmit data to untrusted third parties, for example, to a remote X app for analysis without revealing sensitive information. These are all part of the, let's say, monitoring system that we're designing. Now, in terms of, I talked about in autonomic networking, and this is basically targeted through an architecture that employs, on one hand side, a lightweight and intent-based service management and orchestration layer, motivated by the, or think about it in the ORAN specification, the SMO layer extending up to the core, and complemented with distributed intelligence, control, basically moved to more closely to the network nodes with the use of multi-agent systems. And why multiple agents? Because they're natively accommodating network intelligence. In that sense, we can natively accommodate network intelligence closer to the user plane in order to be able to support faster and more coordinated decision-making. In addition to this, this R6C also employs DLT, distributed ledger technology, as essentially zero trust mechanism at different levels of the architecture. At the higher level, at the SMO level, we use DLT for dynamic federation of services across different administrative domains, whereas, for example, at the site level, at the multi-agent system level, we use it to secure the proposed mask-based approach through an appropriate infrastructure agnostic software security framework. Now, these are the main innovations that we're proposing. So why Desire 6G? What is the difference basically between Desire 6G and the other projects? Essentially, we study how deprogrammability, which is essentially the capability to program the network fabric both vertically from the control to the data plane and horizontally, end-to-end, from the radio to the core, how this deep network programmability can help us in addressing very challenging use cases and KPIs and meet challenging KPIs, how it can be used to support cloud-native deployment of network services and components, and also how this kind of multi-agent based system and native AI across all layers of the network of the 6G system can address essentially the use of multi-agent based system can address scalability issues that are inherent to more centralized control and network optimization. And of course, the goal is to put this together as simple as possible, exploiting, as I said, other innovative methods like AI-driven telemetry or DLT for federation or for securing the agents. Now, I'm going to start with a brief overview of what we mean by motivated by the discussion from Peter. I will just also describe what we did by service in Desire 6G, and then I will go into the architecture. So essentially, we assume that we have two types of service in Desire 6G: an end-to-end service, the edge-to-edge service, which is the inherent legacy service from the UE to the UPF to the PDN. And on the other hand, we also consider an end-to-end service, where essentially the service graph includes also applications from the UE app to the corresponding edge app, which means essentially that the entire end-to-end path is controlled by the D6G system. And this is, we propose this as more preferable for latency critical applications. Going into the architecture, you see basically the colors correspond to different highlights that we saw in the D6G innovations. So essentially we have a D6G site that reflects the basic architecture. In blue is highlighted the network intelligence and control layer. You have the deprogrammability layer, which is with pink infrastructure, and on top, in a more centralized solution, you can have the service management and orchestration layer. That is basically the green one, which is essentially responsible for end-to-end service lifecycle management, including service provisioning, deployment, and any kind of non-real-time service optimizations. Now, it also, of course, to do this, it contains a number of modules that are responsible for these different tasks, and it is a main interface towards an external world. Now, what do we have in the SMO? We have intent-based service management, which essentially pertains to SLA to intent translation to service template translation, which essentially is then uploaded. Loaded into the service catalog that stores the description in the form of corresponding service graphs with the necessary parameters, like quality of service, for example, related parameters that are necessary for deployment, and service assurance in the following. We have components like the optimization engine, which is critical in order to support machine learning operations, artificial intelligence and machine learning operations pertaining to the automation of service deployment and lifecycle management. Now, essentially, for example, during the initial deployment of a service, the optimization engine can receive the service request in the form of an RDF or an RDF graph, annotated with the corresponding respective SLAs, and it's a responsibility of the engine using some appropriate machine learning model to split it into the corresponding technology segments and decompose the corresponding SLA in an optimal way. And of course, you have the service orchestrator that is responsible for service deployment and all the next steps pertaining to service assurance that include the SMO. Now, orchestration may take place. Basically, the orchestrator is useful, as I said, for service deployment, but also we also support a more dynamic type of service, where essentially you may have a network service deployed across an area, and a UE that can participate, can trigger the creation of the partially deployment of a service in an area that is not covered. So it's a more dynamic way. Let's say we also propose a more dynamic way for service deployment. You have components like the machine learning function operator, which is in charge of creating AI/ML pipelines and relating them to the target service that we are deploying. So essentially, it is used for deploying the agents for a given service. And a number of components, like standard components like data lake, which is basically supports storing, monitoring, and topology information that is used by the SMO layer at this higher layer. And also additional, the federation service, which is responsible for managing multi-site deployments of a service. Now, the SMO is essentially, of course, for those of you where we are working in the ORAN area in particular, the intent-based network management, intelligence orchestration, and essentially AI/ML workflow, these are done by the optimization agent and the MLFO, are essentially covering non-real-time link functionality in the ORAN ecosystem, which is basically responsible for generic optimizations on medium to long time scales. Now, moving one layer down, so now we're focusing on the deployment of the Desire 6G architecture in each Desire 6G site, which can be a cloud, a more centralized cloud center, or an edge site, where essentially you have the optimization, highlighted in blue, as I said earlier, the optimization and network control layer, where the control plane logic and the optimization logic essentially reside. And in our case, service optimization, for service optimization, we propose the use of, as I said, of the multi-agent based system, that where essentially the agents receive service-specific monitoring information and are responsible for fine-tuning the network and compute resources through the rest of the components like that we will see later on. Furthermore, the multi-agent system for the service, it also configures and uses the pervasive telemetry system to receive service-specific performance indicators. In that way, we have a more dynamic, let's say, monitoring service. When we need additional probes, we kind of deploy them. For example, in order to get some end-to-end latency for latency-sensitive services. Now, essentially, this split that we have between the more centralized SMO and the more, let's say, the distributed part of the multi-agent system per service, promotes, in our case, service assurance through enabling faster control loops closer to the infrastructure, ensuring also the scalability of the system, as essentially its self-operation relies mainly on the autonomous operation and the coordinated operation of the service agents. Now, as I said earlier that one of the main propositions for Desire 6G is the use of an end-to-end programmable data plane. And why? Because it is important for us that it allows, apart from flexible, also customized packet processing operations, as well as the use of fine-grained network telemetry solutions through in-band network telemetry. Now, in the pink box, basically is highlighted this data plane programmability layer. And there, first, let's focus a little bit on the different network functions that we have. Okay, so essentially, network functions are split into the control plane and the corresponding packet processing data plane logic, which you see on the right-hand side in the figure. Now, essentially, the main role of the control plane, of course, is to configure and update the objects like tables and registers and whatnot in the corresponding data plane function. Now, between them, we see that the infrastructure management layer, which is essentially an abstraction, hardware abstraction layer on steroids, in my opinion, that serves as a bridge between the two, hiding, let's say, the implementation and deployment details from the control plane by essentially providing a simple and unified view of the data plane, of the data plane functions. And these functions should be able, as you see here, to be run, to be ported between different hardware targets. Now, we have a number of different NFs that exist on the D6G system. We have the standard business logic NFs, the green ones, which essentially execute packet processing steps that are dictated by the given network service. Could be, for example, the basic components of a mobile network of a mobile network system. It can be also, but we also have infrastructure NFs, the red ones, which essentially execute steps that are done automatically and independently from a given service. These are functions that are used by each and every service, and they're responsible for routing, there are transport adapters that can perform load balancing or support all the cloud native operations pertaining to the NFs. And now the infrastructure management layer, as you see, is quite pivotal, is quite central to the desired 6G architecture, as it is responsible for a number of things. It supports essentially, as I said, that it supports the cloud native operation of the system by allowing essentially transparent scaling of network functions. It also allows us to offload transparently, functions, to offload them to different hardware accelerators, depending on the requirements, for example, the SLA requirements of the service, or depending on the load of the network at the time or whatnot. It enables multi-tenancy support at the data plane. How? Essentially, it allows multiple data plane network functions to run on the same hardware by aggregating their respective data plane functions and exposing an isolated view for each of them to the respective control plane elements. It allows us to adapt. It allows the traffic to adapt to non-programmable data plane programmable domains. That can happen when between, for example, desired 6G sites, where there is a non-PDP transport domain. In that case, we need appropriate encapsulation. This is handled by the IML for tunneling between the two sites. And the IML also performs all these different kind of optimizations at this level. For example, it can do transparent offloading of heavy hitter offloading to different performant to a performant hardware for NFs that can run on different on multiple targets, or it can support, as you see here, as right here, optimal routing between. It can optimize the routing between different network NF data plane network function DPs. By essentially collocating them, all right? So by doing NFDP aggregation. So it has a number of, let's say, capabilities, a number of, that's why I said it's like an abstraction layer a bit on steroids. Now, apart from this, you also have a number of components like standard components like the virtual infrastructure manager. In our case, is Kubernetes that is responsible for managing the compute resources of the desired 6G sites. And of course, as I said, the physical infrastructure, where we have compute and networking components. Some of them are programmable, some of them are also non-programmable hardware entities that can be used by different functions. Now, depending on the site, depending on the functionality of the site, we can have, of course, different hardware. And here, here we have a more, let's say, centralized site, but here we have an edge site where you see additional components pertaining to the radio resources. With an additional set of run NFDPs, data plane network functions. Now, having said that, I want to go just a little bit on the programmable data plane layer, and then go up a little bit to the multi-agent system in order to show again to kind of highlight the differences in the different loops that we have for optimization, control loops that we have. So I also saw a different figure earlier, where essentially we have on the left-hand side, you see here, you can see that we have a network function, whichever network function, whether it's a mobile network function or some application function, it can be split into the data and the control plane entity. So the data plane can be executed in a number of different targets, as you see here. We have ASICs, CPU, GPUs, and whatnot, in addition to the traditional CPU resources. Now, IML, which basically runs on the host or on a Kubernetes pod as a service, can act, will act as a proxy between the control plane component and the corresponding data plane component of the network function. And in that sense, it allows the IML to carry any kind of seamless optimization that we want in the data plane. For example, we will see in the next slide that we can run, the IML can instruct to run multiple instances of the same data plane component and distribute the load between these two different data plane instances. Now, the communication channel between the NF data plane and the IML is before runtime and the corresponding and over gRPC, and between the NF, the control plane, and also the AML, again, we use before runtime with some additional annotations that are used for the data plane optimization. Now, on the other hand side, the NF control plane on top can use any kind of custom protocol or for its northbound API to communicate with other components, like, for example, standard 3GPP control plane functions. Now, this is an overview of how this, let's say, the IML and this split of the data plane control plane functions and can allow, allows us to provide a more cloud native approach for the network's functions and components that run in the network service. So functions essentially, as you see here on the right-hand side, should be spawned and turned almost instantly. And what we have is we have the logical view on the left-hand side of a network function with the control plane and the logical network function data plane. And on the right-hand side, we can see that the IML essentially can optimize the data plane by, on one hand, selecting the appropriate target where it will run the NFDP, but also by spawning, by creating new instances of the same data plane function. Now, if the control plane delegates a rule to the corresponding data plane object, it's the IML responsibility as the proxy to decide to push the corresponding rule to the appropriate data plane instance. And here, we have the high-level overview of the load optimizer infrastructure NF. Now, this happens at the data plane at the PDP layer. There is, as I said earlier, there is an additional layer of the multi-agent systems, where essentially these operate and are also at near real time. And to explain a little bit the mass functionality, assume that you have a communication service, as we see here on the figure, that spans the run and transport network. Now, what we have is part of the architecture. We have the service agents, the multi-agent system for the service that is running on top of the service, and we have for each site, for each basically, you have an agent per service per site, and on top you have the SMO. Now, basically, the service agent on the first router in the path will receive the maximum end-to-end delay that needs to be ensured, an initial budget delay from the SLA decomposition process that happens at the SMO of the initial partitioning of the service, and a set of routes that adhere to the budget delay that can be used for the connectivity service and the corresponding policy that we want to apply. For example, the SMO can instruct the service to set up the agent to set up the most cost-efficient route at the beginning of when the service is deployed. Now, in this particular case, we see that we have two routes, the orange and the green one, and assume that the orange one is, let's say, the shortest path. Now, the service agent that is running, that is controlling basically the corresponding elements of the service, and in this case, the first router and the path, can use any kind of intelligence like DRL to dynamically estimate the portion of traffic that can be forwarded via the different paths. Now, how it is done? Essentially, the model is pre-trained and is loaded into the service agent, into the DRL agent, and as we have through the pervasive monitoring system, we have continuous, let's say, performance indicators measured and distributed between the agents, which allows essentially, on one hand, to make appropriate decisions, but on the other hand, also the corresponding model to be updated with the decisions that are taken during network operation. Now, at some point in time, let's say you see on the left-hand side, you have the traffic over the hours of the day, and we see at some point we have an increase in the corresponding input traffic. Based on the model of the agent, on the first router, the path routes, part of the traffic split, instead of just from the orange path, between the orange and the green path, to meet the corresponding, to keep the delay budget, to keep the requirement for the delayed budget that we have. So this is essentially where how the multi-agent system enables, let's say, near real-time control optimization. Now, I'm focusing a little bit on the desired 6G sites, in that sense that I'm saying that all these functionalities, data plane programmability, pervasive monitoring, in the information, the multi-agent systems that are running. So you have a lot of control, basically, which is done at the desired 6G site level. Now, what happens, which essentially will allow us to meet extreme KPIs, as I said at the beginning. Now, in order to interact with the transport network, assume that we have also we basically assume that we have an SDN controller that and appropriate information through a monitoring system. But we can also have, we started motivated by the work that is done in projects like Predicted and Deterministic, we look into how that net can be used as an extension for desired 6G. And in that sense, for example, we can replace or we can use a DetNet-enabled transport network in conjunction with a more, let's say, strict or a more controlled desired 6G sites to meet the corresponding low latency and high reliability KPIs of an application, of an end-to-end application. Now, what is, with 1 minute almost to go, so what is the takeaway from the desired 6G presentation? So basically what I was trying to explain is through the architecture that how is service assurance done in desired 6G in order to meet such extreme KPIs. We have essentially 3 basic layers that act automatically in their own area and instruct lower layers to gather information and modify settings or deployments. Of course, at the forwarding plane, at the forwarding level, we investigate programmable traffic management with the goal to prioritize traffic flows and optimize resources. And in that sense, we're also looking into aspects of, that's why I said programmable traffic management, because we're looking into aspects of how we can optimize or we can change the scheme based on the requirements or the updated requirements of the network services or a particular network service. Going on level up at each technology domain, essentially, we have a number of different controllers like the near real-time RIC, the SDN controller and whatnot, and the IML for the compute resources that essentially, and the rest of the hardware resources that essentially execute local optimizations in an attempt to solve local problems. For example, resource outages or overload situations. Now, in the run, for example, you see here we have a near real-time RIC that can execute local optimizations pertaining to policies like power consumption optimization, or the IML can be used, for example, apart from handling compute resources through the Vim, it can also control hardware units, like spawning, as I said earlier, spawning new instances of NFDPs through the peer-for runtime interfaces and perform local optimizations. We have one level up, the MAS, the multi-agent system deployed for each service that works on service level optimization by collecting information from the lower layers, and in particular, communicating with the near real-time rig, the IML and whatnot, and the SDNC, the controller. And at the topmost layer, we have the SMO that reacts to problems if it is triggered by the lower layers like the MAS, or if there is an update, for example, in service description. And this, we try also to map them to the corresponding time scales that we see in ORAN and relevant specifications. That's it from my side. Thank you very much. Any questions?
Thanks very much, Krisa. Any questions?
Yeah.
Yeah, you did it very well. So there is another question in the chat. I will read it. Since many 6G real-time applications such as URLC require a delay less than 1 millisecond, is it possible to fulfill these requirements using this approach?
We are looking into it. The initial problem that we have is that the applications, the use case that we looked into, basically did not have this kind of extreme requirements. And I'm talking about immersive application and the corresponding the particular digital twin. Now, we believe through the aspects of programmable TM, basically through programmable real-time control, we can address this kind of requirements. But as I said, it's a topic that is currently under investigation.
Okay, thanks. Any other questions? If not, I guess we can go to the next presenter. So thanks, Krisa, again.
Carlos, there are two other questions in the chat.
I only saw.
I see Shakil Ahmed.
Yes. Sorry. That question I think just pop up.
And I post one, but you can skip it.
Okay. So do you see the question, Krisa?
Yes.
Have you considered how the future 6G data center may look like with cloudified RAN, core and AML workloads with the GPU, CPU, and ASICs?
I think, in my opinion, this is exactly what we're looking at. How essentially the cloudified RAN, core and AML workloads will run with different GPU and CPU and different hardware targets. And this is why I said I'm essentially mentioning workloads, because this is what the AML the purpose of the AML layer, to kind of enable this kind of deployment and portability between different hardware targets. I hope that answers the question.
Can you hear me?
Yes. Tell me.
Yeah. Thanks. Yeah. No, it was a very interesting presentation. And I was, trying to follow this work because today, if you want to build something, and most of the telcos, what they are doing, they're building kind of a island of AI cloud. Let's say, we know the most prominent vendor there. So if you want to build something AI cloud, the options is like NVIDIA Enterprise AI, and that's kind of an island or maybe a black box, you can say that. But I was kind of looking into in future, if you want to Kubernetes, probably everybody agrees that that can take most of the workloads, RAN, core, and also AI workloads. But then how we could unified with all those different kind of hardware underneath, and maybe I'm not referring to a common cloud that would kind of handle everything, RAN, core, and AI, but maybe kind of uniform. Let's say maybe we unified on the Kubernetes distribution layer, that we use the same distribution on on this different kind of cloud, so the telco have less problem for manageability. That's what I referred actually.
If I understand correctly your question, because I might not get exactly the point. That's why I'm talking about the hardware abstraction layer, the corresponding hardware abstraction layer in NORAN, or what we call infrastructure management layer, which is more, let's say, has extended functionalities that allows this kind of, let's say, uniform access to different, or flooding to different hardware. Whether we're talking about workloads pertaining to AI, whether we're talking about workloads pertaining to the traditional network functions or whatnot. So
Yeah.
also it entails different hardware vendors and implementations.
Yeah. I guess, like we need maybe a longer time than it would be allowed here. But yeah, thanks for the presentation. Maybe we can sync up later.
Sure.
Thank you.
Okay, thanks. So we have still 2 minutes. So maybe the question from Antonio: what about deterministic services?
So deterministic services per se, that is a question. So you have this question also in the panel later on. So what is the difference? We see two approaches: deterministic .NET and this kind of approach with programmability. So we believe essentially what we are promoting here. We believe that this kind of strict requirements that can be mapped, can be met without necessarily the complexity or the additional, let's say, cost that entails a .NET or a TSN implementation. But using this kind of standard packet level kind of services. And we can employ .NET for a more, if needed for specific domains where we cannot, where we don't have this kind of, where deep programmability is not supported. That would allow us this additional axis of control.
Okay, thanks. So there is another question. If you can handle that in 1 minute, is there any mapping between .NET at the network layer and TSN at the MAC layer?
This is not for us.
Yeah, I think this is more for Peter and Antonio.
Yeah.
So let them move to the next presentation. So Joachim, I guess you are starting, right?
Yes. Can you see my screen? Does it work?
Yes, we can.
Very good.
Thanks.
So, good morning. My name is Joachim Sachs, and I will say something about deterministic, or work that we do in deterministic 6G, looking into analysis of latency in 5G and possible improvements. And this presentation will be by myself. I'm working at Ericsson Research, and Gurov from the Royal Institute of Technology in Stockholm, KTH. And with that, I get started. So I will start with an introduction, then we will have a review of latencies as we see them in a 5G network. And then we will say something about the approach we take in deterministic 6G before coming to a summary. Right. So, I mean, the motivations where we come from is we see that we are increasingly moving towards a cyber-physical continuum. Digitalization is driving the transformations of society and industries. And that means we see new forms of interactions that lead to this cyber-physical continuum, where we have on one side the physical world that is connected to a digital representations, and there's interactions in between these two. And we need end-to-end dependable communication and an infrastructure for that to enable these interactions and provide support for these interactions. Now, when we think of dependable communication, so what is the little bit taking a step back and saying, where do we come from? I mean, over the last decade, there has been quite some work on looking into low latency and reliability in communication systems. I mean, historically, this is an area that has been driven very much from the automation industries, which have also developed a plethora of many different proprietary real-time field bus technologies and real-time Ethernet variants. But this has some 15 years ago started to be really being addressed in the standardizations of the Ethernet standard itself by adopting time-sensitive networking as a real-time extension or deterministic extension of Ethernet. This was similar approaches have then been added in IETF, in .NET for providing similar functionality on the in managed IP networks. And we've heard a bit of this in the presentations before. And then, of course, with 5G, also ultra-reliable, low-latency communications was being introduced into wireless networks. And this standardizations there started 2016, first release being ready in 2018. And there was explicit support for TSN and also .NET then also integrated into this 5G standard. And this is, as I said, the driving force for a lot of the low latency dependable communication schemes come from the drive in the automation industry, which is where Industry 4.0 development is basically one of the motivators for that. What we also see is that there's now an increasing adoption of OPC UA and its extensions to field level communication, which is basically the bridge that defines how the application developers basically can write the application, and that translates to the usage of for example, time-sensitive communications. So I think we see that there's in total quite some momentum in the direction of looking into dependable communications. So when we think of our project Deterministic 6G that we are presenting here now, there we have the visions of setting the foundations, the technical foundations for future global communication standards that enable dependable communications. And if we look at this, so let me see, I hope you can see, oops, let me take, maybe you can see my pointer. So we have on one side kind of the development which happens in the wireless space. So we have 5G advanced, we have 6G, where time-sensitive communications and ultra-reliable low-latency communications are topics that are being addressed in the standardizations. And we see at the same time the standardizations that is ongoing more on the wire technologies, time-sensitive network, deterministic networking. And we see that we want to bring these two worlds together in a way that they jointly provide optimal, dependable communications, also with 6G that allow innovations in vertical use cases. And for this, we have in this project set up a consortium where we have several players which come out of the automation industry. We have BNR Automation and ABB. We have the Scuola Superiore in Sant'Anna in Pisa, and a spin-off of Sant'Anna, which UVO, which both look into wearable robotics. We have partners from the telecommunication industry, Ericsson and Orange, and smaller partners like Monty Marsh and Kumukor. And then we have leading universities and research institutes which contribute with their specific competence. And in this consortium, we are looking into how to address the challenges that I mentioned before. Now, taking a step back, where did we start from in the 5G ambition? So 5G was targeted for addressing different directions. So one is, of course, the enhanced mobile broadband, which means very much on being able to provide very high data rates for being able to transmit large data volumes. But from a latency performance, it's very much based on best effort latency. There's the approach toward these supporting sensor technologies, massive Internet of Things communications with simple devices with extreme coverage and long battery lifetimes. And then there's this corner on ultra-reliable low latency communications that shall enable critical IoT services, the industrial Internet of Things, time-critical communications where consistent latency, high reliability and availability is in focus. Now, time-critical communication means that we want to change the characteristic of the communications, where if you look here in this graph on the latency that is perceived over the communications from the applications over the network to the receiving side, where we see how the latency is perceived from the applications, where in typical mobile broadband networks, I mean, the average performance and latency is kind of important for improving the data rate, but there's no focus of providing a bound. And time-critical communication means that we want to be able to really provide an upper bound of this latency with a reliability that basically decides or specifies what is the probability of not being able to meet this bound. And this latency then appears over the entire end-to-end chain, which in the case of 5G means we have to enter the 5G network at some gateway, the user plane function, UPF. Then it goes over a transport network to a base station, the G node B. We have the radio interface to the UE. Then there are also UE processing latencies in the device itself. And then it goes to the applications. And there can be even between the applications and the UE, or between the applications and the core network, further networks, like, for example, TSN networks. And this is basically the range that needs to be addressed for time-critical communication. And looking at the application a bit more here, and the locations of where such an application can be. I mean, first of all, the applications, we want to be able to support applications according to our specific needs. So one important part that 5G and mobile networks introduce is a virtual service concept that allows to specify different traffic flows for different applications, separate them, and allow to customize and improve the optimize the performance for these different virtual service flows to have the dedicated treatment according to the needs of a specific traffic flow. And now I come to the so where are these applications hosted? If we look into latency that is induced by distance, we simply have the laws of nature, speed of light, which means if we want to have an application that is running on a server or on a cloud somewhere very far away, then we simply introduce latencies by the time that it takes for signals to travel over this long distance in a fiber network, for example. Which means if we have servers hosted somewhere on a national level, then this can by itself introduce some tens of milliseconds of additional latency in the round trip time. If we are beyond what is the pure radio latency, and if we come more to regional data centers, this is reduced. But with edge computing, it's possible to bring these computing platforms closer to the end user. And if it's at the edge sites, we are at a low single-digit millisecond level. And of course, it's also possible to bring this on the site if we have deployments in local area. So this is where, I mean, we have to think of where is actually the application running end-to-end, and edge computing being a capability for reducing the latencies by bringing the execution closer to where it is needed. Then on this local deployments, there has been quite some work in the standard for supporting LAN communications with the 5G standard, and explicitly working on the integrations of the 5G system with local networks based on time-sensitive networking, Ethernet and time-sensitive networking. Now, when we look into reliability versus latency, so I mentioned before that we want to be able to provide a delay bound and that the latency stays below this bound. But what we see is also that there is still kind of variations of the latencies, even if we meet this bounds. And there are several reasons for this. We see a bit more of this a bit later. But one of them is, for example, that in most of the 5G deployments happening in mid-band or high-band, where time division duplex is used in the spectrum domain, which means there's an alternative pattern on slots in which transmission is happening in the downlink, so from the network to the mobile device, and then it's alternating with the slots where the device can transmit in the uplink to the network. And depending on when packets arrive in uplink or downlink, they have to wait for the next opportunity where they can transmit. And this introduces, for example, some frame alignment delay, which causes some variation. But what is also happening in the mobile network, I mean, a wireless communication system is something which is kind of has in its nature some fluctuations of signal strength due to reflections, blocking, and so on. And so in order to take care of packets that do not that are not received correctly in a first attempt, there's the hybrid ARQ mechanisms, which is a retransmission mechanisms where if a packet is not successfully received at the receiver side, that it is in a fast way retransmitted. And this is also a very effective way for providing reliability, but of course it comes at a price of an increased latency. So what we see here in this that we have multiple transmissions which jointly then provide or increase the reliability to come to a certain bound, but it depends then, but it introduces latency, as I said. And there's a trade-off here that needs to be considered, and this has to do with spectral efficiency. And that means it is possible with some of these standardized features to reduce this latency by basically making sure that the first transmission is more robust. But it also has to be understood that if we take a look into how a wireless signal is transmitted, there are variations which lead to fast changes in the radio signal and in the radio signal strength and quality. And typically, if we take an operation point that is used for mobile broadband services, for example, you make sure that you have a very efficient kind of modulation scheme that allows you with a very high throughput. And then occasionally you have some dips where you cannot meet to transmit at this rate, and then you may have a loss that is then a few milliseconds later retransmitted, and thereby you get the packet through as well. If you have a video download, this doesn't make a big difference. You don't even notice it as a user, but you have basically a very high throughput with this operation point. If we want to make sure that the first transmission is basically error-free, we have to add margins to this operation point, that the probability that you have errors in your first transmissions become very low. And this comes then of this cost that you have to accept that there's a significant decrease in the spectral efficiency, the more reliable you want to be with your first transmission. So this is a trade-off that needs to be traded against each other. And in some other, 5G introduces a toolbox of functionality in order to provide the higher reliability and lower latencies, like pre-scheduling and configured trans, mini slots, flexible numerology, this fast hybrid ARQ that I talked about, fast retransmissions. There are preemptive transmission schemes. There are robust control and data channels that have been introduced, redundant connectivity and multi-antenna diversities. And depending on how these toolboxes are being used, there are different latencies that are achievable, depending on if you use retransitions or not. There's some other, in another project, we did some work on looking into several of these options on the latencies that are achievable. So it depends a little bit on the configurations of the toolbox that is available. And there's quite a bit of more material on those also presented in the references here. Now, with that, looking into more the radio access network, when we have Ethernet or IP traffic that is transmitted end-to-end over a 5G network, then there are 3 user plane nodes of 5G that are part of this communications. As I said before, that is this user plane function, which is basically the gateway node in the core network. Then it goes via a transport network to the base stations, the G node B. And then we have our radio protocols, which are listed here, ESTA, PDCP, RLC, MAC, and the physical layer for transmitting the data over the radio interface to the device or from the device to the network. Now let's look a little bit on where are actually the latencies being introduced in this in these radio protocol stack. And the largest contributions come in the physical layer and the medium access control layer. And they come, for example, if we do these fast retransmissions, they introduce this retransmission rounds with a latency component. But as I also mentioned before, it's this TDD pattern which defines in at least some of the spectrum bands used for from 5G how the transmission opportunities are available in the uplink and downlink transmission. It has to do with how the structure of the frame is structured, how resources are being assigned to a device that wants to receive data or transmit data, and if we do not separate the traffic by giving it higher priorities, and there's a lot of contentions by different traffic flows for the same transmissions, then there's a certain queuing delay that can be introduced. And in some cases, depending on what optimization schemes for handover is being used, there can be some interruptions even from handover. At the higher layers, there are retransmissions which are being introduced in the radio link control protocol, and they increase significantly the reliability if they are configured. but in particular, if the lower layers are configured very reliable, as I said, this is a toolbox that you can configure in a specific way, then there's less need for retransmissions on this RLC layer because they take much longer time than the fast retransmissions that are being handled in the MAC layer. And finally, there's the packet data conversions layer, which basically can introduce some latency component by reordering of data. The packet data conversions protocol allows, for example, so what can happen is that if we have two packets and one needs the retransmission and takes a little bit longer, then it can be overtaken by the next packet, which is transmitted error-free in the first go, and is thereby faster. And it can be configured that the 5G system delivers packets only in sequence. In this case, the faster packet would need to wait for the slower packet, which was first in line, to be received. And that is something that can be configured. And this is also important. Under the PDCP layer, it's possible to apply dual connectivity, which means you duplicate the data and transmit it over two different radio channels of which one may be a bit faster than the other one, and then you make sure that you reorder this. And if this is activated and configured, then this can add a further delay in for reordering. So this was now a quick walkthrough on where do the latencies basically are being introduced in the system. When we look a little bit into networks as we see them, then we see, for example, on the left-hand side, the measurements from a 5G network. We see the typical latency latencies for the packets are in the order of 4 to 6 milliseconds, but there are, for example, here's a case where some retransmissions occur, and there are some cases where, so in this particular measurement setup, we saw over a longer time period that the latency was somewhere between 3 and 17 milliseconds, which means there is a rather large packet delay variations, even if the majority of packets has a kind of confined peak here in the lower side. Ultra-reliable low latency communications is something that has been specified. It is not found so much in commercial deployments today, but this we have, when we look into trial systems that we use, that we see that this can significantly reduce the latencies, but even there we see that there's quite some packet delay variations that is left. Now, talking about packet delay variation, so time-sensitive or deterministic transmission is very much about receiving the right packet at the right time. And if we have now packet delay variations, that creates uncertainty in packet arrivals. And as we have shown in a report that you see there at the bottom listed, uncertainty in packet arrivals can be problematic, for example, in time-sensitive networking, if you want to make use of these time-scheduled transmissions that have been specified there. So one approach that we are investigating at the moment in Deterministic 6G is, can we get can we compensate for these for this jitter, these variations that is being introduced in the packet delays, and thereby, for example, compressing our latency variations into a smaller time window. And this could be done by adding some de-jittering at the receiver of the system, and then you have the trade-off of allowing to have communications with a bounded packet delay variations, and by applying ultra-reliable low latency communication features together with this packet delay compensations, you can basically target different delay targets. The more you come to lower delays, the more you have to invest in or suffer in spectral efficiency. The more to the right, we have a better spectral efficiency. But in any case, it's possible to combine it with having this transmission with bounded packet delay variations. And that is something that we investigate right now. What does it bring in terms of end-to-end performance, for example, in TSN networks? And with this, I want to hand over to Gaurav.
Okay, thanks, Joachim. So until now, we have looked at quantitative assessment of delays in 5G system. Now we are going to give you an assessment quantitative assessment of a 5G delay. But before I present that, I will give you an overview of the delay decomposition model of the 5G system. So on a very high level, we can see that the delay in a 5G system comes from the core network and from the RAN. And mostly in the non-public deployments, the core network does not span over large distances, and it is wired. So this delay contribution is very small and is usually can be assumed to be fixed as compared to the RAN delay. And RAN delay has the radio interface, so that is where the most of the packet delay variation is coming in. So now we try to decompose the RAN delay into further components. And the first component here is the queuing delay. And what we denote in this queuing delay is the impact of having data backlog in the RLC buffers. So this backlog will delay the newly arriving data to be sent to the MAC layer. So that is why this component will introduce delay. And also, as Joachim mentioned in his presentation, that due to the misalignment of packet arrivals with the transmission opportunities, there is some delay, and that delay is also included in the queuing delay. And now the rest of the RAN delay is we denote by link delay, which is further decomposed into three components. The first component is the segmentation delay. The segmentation delay comes from the fact that if we want to send a data segment, there could be a transport block size that is smaller than this data segment. So we cannot send this data segment in one transmission. So you'll have to send this data segment in multiple transmissions, and at the other end, at the reception end, we have to do the reassembly of these segments, and that causes an additional delay. The second component of the link delay is transmission delay, which includes all the delays on the physical layer, the delay caused due to encoding and decoding and so on. And finally, the last component of the link delay is the retransmission delay. So as we normally operate at a certain target block error rate, so we always have likelihood of data segment not being received correctly or corrupted or lost. So we have to resend these data segments, and these retransmissions also cause additional delay. Okay. Now, to do this assessment, what we did was we built an experimental setup of a 5G system, and this setup is based on open air interface and software-defined radios. So all the open air interface functionality running on different hosts. So all these hosts were synchronized using a precision time protocol, so that they have the same timing reference, and that helps us in the making sense of all the timestamps collected on different hosts. So what we did was in the open air interface functions at the UE, at the G node B, and at the UPF, we inserted the measurement points at different layers of the protocol stack, and these measurement points were responsible for timestamping whenever they receive or send a data segment. And so with these measurement points inserted, we use a traffic generator to send packets from the client to the server in the uplink direction, and we timestamp these packets in open air interface, and these timestamps are then sent to a database for storage, and then we can further perform advanced analytics on these stored timestamps.
Should I go on?
Yeah, next slide.
I think here it was planned that we would have now a video, but this didn't work so well with sharing, so we have some screenshots instead.
Right. So these screenshots are taken from a live analytics done on the data collected on the setup that is shown on the left hand side. So all the timestamps collected from the experimental setup are sent to this database, and the analytics that you see on the rest of the screenshot are derived based on that data. So first, starting with the middle one, here we plot the complementary cumulative distribution function of end-to-end delay. So how to interpret it is like this. So at a given delay target, we can at the y-axis gives you the probability that the end-to-end delay will increase this x value. So at certain at certain 15 milliseconds, you can see the probability of exceeding is about, I think, 10% or something like that. So this is how you interpret the CCDF, and it turns out to be quite a useful visualization to say if our 5G system can support application requirement at a certain latency reliability level. Okay, and on the right-hand side, you see the different time series plots for the end-to-end delay, and also the subcomponents of this end-to-end delay. And on the left-hand side, we have the pipe chart for the breakdown of latency at the average. And in the middle, we have the latency breakdown at the of all the packets that experience delay more than 15 milliseconds. And one thing that we can clearly see here is that for all the packets that exceeded 15 milliseconds, the major contribution of latency is coming from the retransmission delays. And yeah, this is what we also expect. Okay, and now we can switch to so this is another screenshot from the same setup, so now this data-driven delay assessment gives us nice visualization. It also gives us insights to argue about delays and subcomponents at different targets. But what can we do further on is that we can optimize these delays using the insights from the data gathered. So on the left hand side, we plot again the CCDF for a certain configuration of the 5G system, and what we can see on the plot in the bottom is that in this certain configuration of the 5G system, we have a significant amount of segmentation delay. So there are some segments that are surfaced at in this green distribution, and then there are some segments that are serviced at this maroon distribution. So this is because the extra latency is coming from the segmentation of the packets. And now we try to optimize the segmentation delay. How we can do that is by assigning more resources to this particular flow, and that brings us to the second settings. So here, as you can see in the CCDF plot, the plot has shifted to the left, and also the contribution that you see of the segmentation delay in the green has disappeared, because now all the segments are serviced in their first segmentation. So there is no actual segmentation happening here. And this was one opportunity. And then another opportunity that we found to improve the delay was improving the frame alignment delay. So in the plot, you can see there is still some in the second plot, we see there is some queuing delay involved, and this we found we can remove by aligning the transmission opportunities with the arrival time of the packets. So what we did here was we adjusted the arrival times of the packets such that we experience a minimum queuing delay. and that can be seen that the CCTF plot has further shifted to the left, and we have improved on end-to-end delay a lot as compared to our baseline experimental setting. Okay.
Right. So now, so taking a step back and thinking, so if we think of the requirements of these time-critical applications, then typically we have a requirement of both lower and upper delay bounds. And this is to avoid a failure or degradation of the experience application quality. Now it's often claimed that the deterministic network and application characteristics are a necessity. But if we look into some of the enablers that are really being of interest in the industry today for digitalizations, then they challenge this. If we take cloud computing, suddenly the applications that you put into a cloud environment is not deterministic anymore. It is kind of exposed to variations of compute times that you find in a cloud environment. We have shown before, wireless communications has from its own characteristics some stochastic variance in the latencies that it supports. But we also see an increase in making applications more adaptive, adding machine learning or machine vision in control applications and so on, which means that the applications by themselves become more variable in themselves. And all of these directions basically lead to that there is a certain stochastic variations that is introduced by different parts of these different technologies. And an approach that we are investigating in deterministic 6G is that we say, well, the strict definition of determinism means that basically we can get rid of all stochastic variations in the system, or explained differently, at every point in time, the system behaves in a predetermined way from any input state with a given input. And with these variations that we see in these different components, we see that maybe this elimination of all stochastic elements may not be feasible all the time. I mean, you can avoid using cloud computing and stick to your embedded real-time compute platforms, but then you give up of some opportunities there. So, I mean, what is the way on how to embrace them in the best way? And what we pursue is there a way for embracing these stochastic elements that can be that are not fully predetermined, and make them predictable and thereby plannable for the system, and thereby being able to manage them in such a way that they fulfill the requirements of the applications by using flexibility and adaptability. So basically, instead of saying, well, we simply are fully deterministic, we say, well, we can provide exactly what you need. And thereby transitioning into saying we want to provide dependable communications for time-critical services. And dependable communications here means that we are able to quantitatively ascertain the delivery of the service performance for the communications as it has been agreed. And there are some building blocks for this. So of course we need to provide low latency. I mean, the applications are still low latency, so which means the toolbox for low latency and high reliability are still important. But we also need a specification which clearly specifies the requirement of the applications. And if we introduce then observability for performance monitoring and predictions, we are able to see how well our system performs and how you can map it to if it fulfills the requirements that are specified for the applications in the point before. And then it also gives you the, if you have this full awareness of the network, of its capabilities and where its operation point, it also allows for new ways of interacting with the application domain. For example, that you can provide a warning in case that you simply have a resource shortage and there's a probability that you may not fully fulfill a certain requirement. So this is the focus that we put on, that to be able to enable dependable communications for time-critical services. And with this, how are we with time? I think just right. So a short summary. So we look into the convergence of the digital and physical worlds, where we see a lot of need for time-critical communication in the future. We look into data-driven latency assessment that provides us with the opportunity to design enablers for end-to-end delay optimizations, and also making sure that we can match the requirements of the applications and become a dependable communication system. There, the work that we have shown here is listed in a number of references, several coming from the Deterministic 6G project and some further publications that you can find later. And there's also the website of our project where you find a lot of this material. And with this, we're at the end of this presentation.
Thanks a lot, Joachim. So we have some questions in the chat. Let me see. So there is one question from Jose Fontalvo in the chat. How do you handle the trade-off between the extra latency added by the jittering at the receivers and the low latencies that you expect as URLC code? How have you defined some zero-sum model?
So if we have considered the, what was it, the
jittering at the receivers,
yes,
and the low latencies that you expect as the URLC's goal?
Well, I mean, we are investigating this. I mean, can we remove the jitter and thereby become bounded? And that is basically, let's say, different directions. So, I mean, the low latency, if you have an upper bound, you have the functionality for low latencies, which lets you push down the bound of what you want to be to achieve. But that is, and then it's an independent kind of function to look into. Well, how can we do this with low jitter? So I think they are complementary approaches that together can provide a latency bound together with a bound on the packet delay variation.
Okay, thanks. And I think Antonio was also mentioning in the chat about the latency with the open interface, and whether you can share the reference, the paper where you are reporting all this. So I guess you can probably do it in the chat.
It's the end of the, well, maybe even Gurov, you can put it.
I can paste the link of the paper in the chat.
But otherwise, yeah.
Okay, so good afternoon, Joachim. Thanks very much for the presentation. So now we can move on with and we are perfectly on time with the agenda, with the panel now. So I prepared some questions to drive some discussion. We don't need to go through all of them, and we can also go a different direction if you want, but just for the sake of starting some discussion. This is one question. What do you think, guys, are the main architectural changes, enhancements that you foresee that are required in 6G to enable this, according to the IMT 2030 terminology, hyper reliable and low latency communications? Anyone that wants to start taking this question? No one?
Maybe I can start. Sorry.
Okay.
Hi.
Lisa, go ahead.
Yeah, I've been thinking about this from the Desire 6G perspective a lot. And of course, AI machine learning integration is already kind of being pushed in the standards already. And how we can use, particularly how we can use AI for predictive analytics to anticipate problems in the network or to allocate resources proactively. That is one aspect which I think, at least from the Desire 6G perspective, we anticipate that it will have an impact in addressing hyper reliable latency communications, and essentially we kind of see the AI, the machine learning natively integrated into all layers of the 6G system, going from the top to the SMO down to in network, for example, for doing inference. And in the same direction, of course, the use of a digital twin, which I think is also started to be investigated, I think can provide a safe, and in that sense, and can provide a control environment in order to facilitate, let's say, learning and optimization, during without restricting the operation, that would essentially allow us to meet, to kind of proactively meet, update, reconfigure the network to meet these kind of requirements that come from XURLC.
Okay,
But if I
thanks, Chris.
can add to
Yeah.
this, so I think in general, I mean, I think when we think of the use cases, it is not so that with 6G something will be fundamentally different. I mean, the use cases start appearing today, or they exist already today, and they will continue in the future. And we will see that we start addressing this with 5G, but actually, I would say this becomes more and more. 6G will turn more and more into a general platform for enabling these kind of critical communications, because they become more pervasive in different parts of industries and enterprises and society. And as Chris also mentioned, I think something where we see a change is that that, for example, the when we did 5G standardizations 10 years ago, or the research towards 5G, I mean, this the AI topic was not yet so much on the agenda at that time. So now I think there's a kind of it's obvious that that AI is an important area, and which means that I think a future architecture will have much more fundamental support for data collections and machine learning, but in general, basically having a more observable system. And I think now, if you apply AI or not, I mean, simply being able to have a more aware system of its own capabilities, that is something that is quite important, as we see in this approach to being able to take promises on delivering certain service performance.
Hey, Peter, do you wanna, or Antonio, you want to?
Yeah, I can also add my take,
Yep.
although I lost my video stream somehow. But I can offer the background of Predict6G. So 2 points I wanted to add. So one is the end device involvement. So from Predict6G, we see that if you really want to have a truly end-to-end service, deterministic one, or low latency, or hyper reliable, then one potential weak link in the end-to-end, however smart and performant network gear you have, is that if the end device from the application layer down to the modem and the queues in the modem and in the uplink is not matching the deterministic needs or low latency needs, then that could be a source of issues. And the other thing I consider potential architectural impact is to make multipath the norm, or make it much more easy to have multipath. I mean, truly end-to-end disjoint multipath for those services that require hyper reliability.
Okay, thanks a lot. So maybe we can move to the next question that I think has been partially addressed by Krisa in his answer, because I was proposing to ask you guys, how do you see the role that AI might play in the future architectures to improve reliability and availability and reduce latencies? Joachim already also touched upon this point about making the system observable to facilitate this. So I don't know if you have anything else you want to add on top of this from Desire 6G and Deterministic 6G, and also maybe Peter, you can add on top of this from Play 6G.
Well, I think it has been, I think, partly addressed before. I mean, being able to observe your system, and then afterwards you can do a machine learning for understanding causality as well. So why is the system, and where is it performing worse or better? That is something that you can have much more analytics in the future for being able to make optimizations in the operations of the network.
Yes, I would also kind of rhyme with the previous ones that, for example, network digital twin, which obviously requires the application of AI models to create relevant abstractions and automation and prediction capability based on a particular network deployment, network data. That is kind of a requirement if you want to reach those low latencies on a scale. So we have to maybe differentiate between the use case when there's just a very dedicated singular service needed with low latency. We can do this today. as much as the intrinsic layer capabilities enable it. But I think for 5G, kind of the stake should be that the scale of these services have to be really high, and that requires automation. And automation would only be possible to adopt this kind of AI models, network digital twinning capabilities.
Okay, if I may add, maybe I'm a bit biased or because I'm working in two of these projects to a certain extent. All this AI and observability, how do you see the involvement from the UE as well as I think has a relevant role? How do you see this when you start having end-to-end different type of domains involved from an administrative or maybe more importantly from an administrative point of view, but also from a technological point of view, because then making observable something that does not belong to your administrative domain and having digital twins, partial digital twins of this, how do you see this problem will be solved or can be addressed in this 6G architecture of the future?
So I think the more heterogeneous technologies are aggregated under, let's say, the umbrella of 6G, and actually it was already partly for 5G with the attachment of WLAN and other things. I think standardization has to play a critical role in creating data models and defining measurements in a way that makes measurements from different technologies, different domains, as well as from different vendors comparable. Even currently, of course, let's say if you think about the 5G measurements, there are a lot of standards. Lot of standardized measurements, which are also defining how the measurement should be produced. So even sometimes formulas are provided that try to define very, very carefully and accurately what that KPI or counter should mean. But practical experience shows that even with that level of definition, sometimes from different vendors, there is implementation difference leading to semantic differences in what the same KPI should work. So I think standardization need to be aligned with the expectation of observability. And the other aspect of that is, of course, the overhead of collecting the measurements and doing the analytics. But I think that is not, that's kind of a different question, not a standardization question.
Okay, thanks. Any other comment regarding this?
Maybe I can add a comment. So we've seen this. We're seeing this in this R6Z, for example. So how this kind of observability of different network segments and to what extent you can pass this information to upper layers for optimization and whatnot. And I think that is why this kind of we also go for this higher separation of concerns between the different domains, technology domains and administrative domains, where essentially you can enable or address, like first responder problems at very fast, with very short control loops, and probably with very easy or kind of not accurate models, AI models. And as you pass the information down, you do aggregations or you kind of change the level of information that the detailed information or the type of information that you send to different layers.
Okay, thanks. Any additional comment you want to add from any of you guys? Okay, then we can move to the next question I propose, that again has been partially addressed already by presentations and the discussion, but anyway, let's see if we have additional comments. So I see that there are two different approaches to this URLC or XURLC. The one that is kind of defined or followed by ITF and somehow embraced by 3GPP on following this ITF deadnet, we can call it. And then we also have the and this will be a bit what, for example, Predict6 is following or adopting, and then the way of deprogrammability to try to enable these low latencies and high reliabilities. So how do you see, and of course you are biased because probably you are following one of these two, but how do you see this in the future 6G standardization? Do you see room for combining both? What are your thoughts on this?
I can also start on this.
Yeah, go ahead.
Yeah, so I think I said it earlier. So I think that there is room for both. Essentially, when you need, you have cost or you need bespoke deployments, then you can follow a kind of TSN or DetNet approach, or where you need more kind of try to meet this kind of requirements, stringent requirements. You can follow a more deprogrammable approach in a more traditional packet switch kind of network. So I think there's cost. It's most cost related. So I don't know how it will go on standardization, or I don't know if deprogrammability or deep slicing in that sense, is something that will be, because I come from the academia, I'm not, very into the standards, but I think there is room for both. That's my opinion.
Maybe to add to this, I think there's a very strong drive towards programmability that we see being addressed in standardization and in industry right now. And this is in particular with regard for making the networks more usable. So it's programmability by providing exposure interfaces, APIs, via which you can put the requirements, you can get information from the network, you can put requirements and configurations or onto the network that help the automation system of the network for finding the suitable configurations. I think this is a very important direction that in particular makes the usability of the networks, increases this for the end developers. Then, I mean, one approach of programmability is there then also going to the user plane node handling. And I think a standard will not and should not kind of specify how something is being implemented. I mean, there's no standard which says a base station has to be programmed in C++ or anything like this. I mean, that in the end, a lot of the product innovations comes by seeing what works well, improving on this, and this flexibility should not be prohibited by a standard. So the standard has to define on how the system works in the interfaces in the interoperable way, so that different components can be provided by different suppliers, the devices, the network, or different network components even, and then make it usable. But then, of course, this programmability also in the data plane also, I think, is an interesting area, of course, in particular in the research phase, when you want to explore something a little bit in a quicker way, prototype something also, then this has a clear role to play.
So maybe I'm adding on top of it or next to it a term self-programmable. So our kind of experience again is that, not necessarily from Predict, is that programmability is good. Parameters exposed is okay, but then you create a complexity that is visible for the user or the operator of the network. So then the next question becomes how to find the right set of parameters that would deliver the outcome that you are after. And therefore, I would foresee progress towards self-programmable / intent-based networking, which is already happening nowadays, with the paradigm that, let's say, it lets the operator define or declare the required outcome, the desired behavior, or the service or management reports or whatever that is, to the network, which, as said before, will automatically deliver that. And that is not contradicting deep programmability, because it obviously requires an infrastructure that can be very well optimized and tailored to different needs. I'm just saying that tailoring, that optimization should be fully automated. And that would actually make networks consumable towards an entity which is not, let's say, telco expert, but which is to integrate telecommunication technology as part of a solution.
Okay, thanks. I have like one or two maybe related questions to the answers that you have provided. So, for example, on this intent-based thing that you mentioned, Peter, how do you see the AI trend on that? Because there are also some efforts going on in the networking community allowing or trying to allow intent-based go a step beyond and basically allow the operator to use just natural language to say, hey, network, I want this to be done. And then all the AI understand what that means, take the status of the network and do something like self-programmable, maybe is what you mean by self-programmability, but
Yep.
do you see networks going that far in terms of how the operators operate the network using AI and this intent-based plus approach?
Definitely, and not just myself. Maybe I can speak that in the EU CNC we actually had a POC in the Nokia booth at the other end of the venue, other end of Predict 6G booth, where we demonstrated exactly what you said. You can type natural language kind of intent or even just a problem statement to the network, and the network responded with what it can do about. So maybe it can offer a service that is solving your problem, or a service that will be providing the right communication output. But it's not just us or me, because even in ZSM, ETSI ZSM, Zero Touch Network and Service Management Standards, you have already acknowledged that natural language can be, not necessarily will be the only layer, but can be a layer of conversation, basically human to network, network to human interface. And with the uptake of LLMs nowadays, of course, not any LLM, but LLMs that are geared towards the technological and domain-specific taxonomy of networking, it is possible to kind of bridge the semantic gap between writing down in English or whatever language some outcome, and then relating that to the capabilities of the network. What it requires from the network essentially is new AI techniques that can capture the semantics of the network APIs, so make the network self-programmable in terms of being able to know what semantical concept in terms of intent relates to which API service, like a slicing capability or a quality of service paradigm is useful for achieving that, and then do the closed loop automation like fulfillment assurance of that one. So new AI techniques, not even a single one. Definitely this is happening, and this is going to happen. A good question is how much of that and what part of it can or has to be standardized. I think that is for the future. Now we see it is happening within research labs, within industrial research centers, yet to be seen in standardization.
Okay, thanks a lot, Peter. Anyone wants to add something on top of this?
Well, I can agree that, I mean, for the usability, a description of an intent, that should be, I mean, if you use a natural language, or it must be in any case be kind of easy to describe what the need is in a user-centric way. And then it's up to the automation system to decompose this intent into the subsystem, what it means for the subsystems, and provide optimizations of the network and configuration of it. So that I fully agree on. I think we are on an automation journey, and the usability of this automation journey must be connected to being able to specify what the end user is actually expecting from the network.
Okay, thanks. So then I think we can go to the last question I have, and I think what is a potentially good way of closing the webinar today. That is about the standardization of 6G. I mean, we have been talking about 6G already for some years. We have projects running first initially like beyond 5G. Now we even call 6G, but still 6G is not completely clear what it's going to be. And starting the standardization of 6G has just started, at least from 3GPP side. So I would like to get your opinion. How do you foresee the architecture of 6G, the standardization of 6G, go in the next few years? Do you expect significant changes, as for example we have in 5G compared to 4G, or do you see this more like an evolutionary type of new G compared to 5G? So comments, opinions?
So maybe from the management angle, because I'm not a radio expert, so I will leave that for more educated colleagues. But from the management perspective, I think that a big step was made already with 5G, making core network service based. But that is not extended yet really to the RAN. And still in 5G, the separation of RAN and core in even standard bodies and the architecture is significant and creating significant issues in terms of, let's say, data collection with end-to-end relevancy, being able to match different types of data into the same end-to-end context. And of course, I don't know what will happen, but what would be kind of a logical evolution in the architecture is to somehow converge the RAN and core or bridge this RAN and core gap in terms of accessibility, manageability, controllability. And it also, to some extent, speaks to the convergence of control/management plane. Because with network digital twinning, we already see that being a bit blurred, because what is that? It's control plane function, or it's management plane, or some mixture of the both. It should not really matter that much once you transition to kind of a service-based architecture, when the right services could be composed into a dedicated blueprint, which is serving a purpose, an outcome, a management action, whatever that is. It should not matter whether that service is actually coming from the radio or from the core. A good example is NWDAF in 5G. That was defined with the effort of bringing analytics into the network and provide value-added outcomes, not just raw data. However, NWDAF was defined in SA2, being a core network function and nothing to do with radio. So as per the standard, we are not able to ingest radio data into NWDAF. We still maintain this kind of collect radio stuff through O&M, and somehow from the O&M maybe you can ingest it in NWDAF. So much better and well-serving architecture would be to close this gap between RAN and core in terms of control and management and data collection and visibility. And that would enable also self-programming and intent-based operation to be a bit easier within the network itself.
Just a comment there. So I just wanted to say I agree with Peter, and we see it already with projects like, for example, this R6G, where they're trying to kind of do this kind of, let's say, convergence in the management of the RAN and core. So it is already an active, I don't know if it is going to be part of the standards or it's going to be, considered in the standards, but this is definitely something that I think also the research community are actively looking into.
So maybe trade from my side. So I think from the standardizations, I think as was mentioned by Peter, I think in particular from the core network, we have made quite some steps in increasing flexibility and allowing introducing new capabilities in the 5G core. So I think on the core network side, I see that very much we will have an extension and of what we have started with the 5G standardizations. Then from the radio side, I think there are quite some new ambitions of capabilities to be addressed. So I think that will be more a new radio technology standard that will have new capabilities. I mean, integrated communication and sensing and so on, that is being investigated there. New spectrum opportunities to be investigated. But I think what I also see important is that I think this data-driven approach, allowing for AI, that is, I think, something that will be a more central part in as the architecture develops. That this kind of a data plane for data collections and enabling that we can have an AI native network design. That I think is also something that we will see more as we go towards the 6G standardizations. Then one point that I think is that I see important is that if we go to standardizations, then I really think that it's important that we what we see, what is it that needs to be standardized. The standard maybe to start with that is not, we have now loads of, I mean, we have here 3 projects presenting their research work, and there are dozens of them, and there's even often the expectations by the funding agencies that they have to make contributions to standards. But I would explicitly say the standard is not the place for document your research results. For that you use IEEE Explorer. So I think the standard is the tool that helps to get the innovations that we have documented in a way that you can bring them to the market and create an ecosystem. And that means that there should really be some kind of agreement on what are the interfaces that need to be standardized. There are so many things that are standardized which never are being implemented. I think it's really now time, out of the good research work that is ongoing, to also consolidate this and align and agree on what of this is it that you really want to bring to the standard, and that everybody adheres to, that you can build commercial products out of this and create commercial solutions.
Okay, thanks a lot, Joachim. I kind of agree with you. I think standardization is basically what ensures interoperability of different implementations to create an ecosystem. And I think that's what the standards should be focused on. So I think we basically get to the time of closing. So let me again thank you guys for these very interesting presentations and for participating in the panel. And before we close, I would like to just call your attention for a quick survey that will help us know what we did well, what we did not that well, or what we can improve. So if you have like 2 minutes, and you can go to the QR code and do the survey, that will be very much appreciated. And with that, we conclude the webinar. We'll start working right now, I mean, in the next few days on planning the next one. So we would like to have like one of these webinars every 3-4 months, something like that, where we can focus on some themes. So stay tuned, and we will announce next one in the next few weeks. So thanks a lot again. Thank you everyone that attended, and see you.